because it's about time, so it's only about 30 seconds earlier. But what I will do, because I am also turning on echoing, so I can actually hear myself, through basically just a loop back. So I'm gonna turn off, okay, right here. So I'm turning off the input capture in OBS. This will only affect the stream to YouTube. It's not going to affect anything in Discord. All right, because otherwise, there will be two channels of my voice. One is through the actual mic, and the other one is through the loopback of the mic, and those two, may cause an issue in the on YouTube. Discord should be fine. Should not be affected by this setting at all. All right, so we are ready to get started with the class. Cool. All right, so I just want to let you guys know that I'm on.
Tech, you have some feedback. Your mic is picking up your loop.
My mic is picking up the loop.
Back to general.
Oh no, never mind. That's your son. We can hear your son in the background.
Yeah, that's him. Yeah, in the background. I think I got the echo canceling turned on already. Let me change the channel. Let me see if I'm using the noise canceling enabled channel in Discord. Give me a second here.
Band.
Yeah, I can hear him too through my headphone.
Yeah, he was just saying the same thing as you, so I thought I was hearing you twice.
It's Richard.
Yeah, I'm already using the echo canceled channel.
Ricardo.
And yeah, unfortunately that is the case. All right, so is that any better? I think my voice is louder in my earphone now. Any problems on Discord?
Sounds about the same. I mean, I can still hear your son in the background. Oh my gosh. But it'll be fine.
Okay.
Nah. I'd rather watch some Prime Slime Rancher.
Yeah, he can project his voice better than I can. All right. So when it does become a problem, I am going to change the gain of the mic, so that way, it's not going to be as much of an issue. He's taking classes too, so he's actually in class right now doing his stuff. Oh, I can see the problem because my mic is turned all the way up. So let me just kind of change the volume of my mic or the gain of my mic until it's more reasonable like this. So I think this helps to kind of remove lesser background sound from the channel. All right, so I'll keep adjusting it if it becomes an issue. All right, so let's go ahead and get on with this class. All right, so the first thing is I do want to let you guys know that I am going to post the scores. You have the scores already, but I'm going to post it. A few things happened over the weekend, actually, since last week. I might have to take on some department chair responsibilities because our assigned or elected, okay, the department chair is actually elected. So the elected department chair has been, I'm not going to judge, okay? I'm just going to say that, things that the department chair is supposed to do is not getting done, okay? So I might have to step up, to take on some of those responsibilities. And that involves, a document that was due like about 2 weeks ago. It's supposed to be a long document. So, yep, things are happening and, it's not exactly expected. All right, so what we're going to do today is to continue with counting, and I might give you the homework assignment, the omega generator, or I might just describe it today and not assign it until Thursday. That's probably what I would be doing, is to give you guys a heads up, and once we get to Thursday, I will give you guys about a week to get it done. Okay, so so keep that in mind. And counting was the last topic that we talked about in this class. And we were talking about permutations at the time. So this was the big mess, and I gave you guys a ungraded homework assignment of omega 3 of something. So did you guys, or did any one of you have a chance to work on that? And are there any questions associated with that ungraded assignment? Did you guys run into any problems? So let me know. Uh-oh, Discord just crashed. All right, get it back into it. All right, so sorry about that. I did not notice that Discord had crashed. And I also did not turn on screen sharing through Discord. So we're gonna start that over here and then go live. Yeah, I saw a few more people getting onto the YouTube side, so I think everything is good now. Let me just take a quick look. Oh, nope, Discord is still not there. Oh, no, wait, it's here.
I see it.
Okay. And I also forgot to turn on my light. So I was in the shadows. There we go. Okay, so I think we're good now. I do need to get back to the text channel so I can see what you guys are typing. All right.
You left off right as you opened it, but I mean, you only asked us if we did the homework, so
Yep.
And the answer is no.
All right, so we are back to the discussion of big omega, and I want to see if you guys got a chance to work on it or not. And for those of you who did get a chance to work on it, I want to see if you have any questions. So go ahead. I'm just going back to the last Thursday's text channel. Completely forgot about. Okay, that's fine. We'll go ahead and work on it today. Okay. So I'm going back, and you guys don't have to go there because I'm going to copy and paste it. So give me a second here to copy the assignment to today's channel. So this way, I can just stay on today's channel. Yeah, we are still on the counting module, so we are still just kind of talking about how to perform counting. And if you look at the text channel right now, that is the ungraded assignment from last Thursday, the omega 3 of Q, K, 2, and 9, Queen, King, 2, and 9. All right. So are we doing okay so far with where we are at this point and what I am about to do? All right. So with no further questions, I am going to. All right, cool. So what I'm going to do is to start up Mousepad, which is just a text editor, because there's no need to use fancy highlighting and whatnot in this case. So I would much rather just be able to type a little bit faster. There we go. So we have omega 3, not the supplement, of Queen, King, 2, and 9. Okay, so we want to know how this is going to expand. So now we go into the definition, and we take a look at how to expand it. So the only time when we don't need to really expand anything, or at least not recursively, is when we have omega of 1. Now we have omega of 3, so we can't really stop at this point. So now we look up the recursive definition of omega I of a set T is expressed as the union of a bunch of stuff, okay? And each thing that we are that is in the union is using one particular element of T, which is coming from this T over here, as quote unquote the parameter. And based on that particular parameter, we are looking at a singleton set made out of just E, the chosen E out of T, Cartesian product with omega I minus 1, and hence this is the recursive definition of T minus the singleton set of E. So basically we're just talking about, okay, everything in T except for E. Okay. So now I switch back to mousepad, and we'll go ahead and use that particular definition. So we now say that this is going to be I'm going to use just uppercase U to simulate the big U notation down here, and then I'm going to use a pseudocode notation, kind of borrowing this from C and C++, and we'll just say that I is a particular element, or E. Okay, E is an element in T. And what does U mean? U is union. In other words, the big U is kind of like a sigma notation for addition, except in this case, the big U is a union over a bunch of things. All right, so it's big U, E in T, and and then the items, each item that we are adding into the union is going to look like this. Okay, it has E, which is whatever we have chosen from T, Cartesian product with omega in this time, and this time we know what we're dealing with omega 2 because I is 3, so I minus 1 is 2, and then the parameter or the set that each omega 2 can make use of is going to be T minus the set of E, which basically is just everything in T except for the element E that we have chosen. So the next step is to expand this. Okay, so we want to expand this instead of looking at this as a loop, okay, which is a little bit more abstract and it's harder to kind of understand what it's going to do, is we basically unfold the loop into, in this case, 4 individual items. So the first item is when E is indeed just the element Q. Okay, so in that case, what we are trying to create is the element of Q, Cartesian product with omega 2, and this time we're looking at T minus E. So that T is it's also not supposed to be here. It is supposed to be Queen, King, 2, and 9. So that is the set T that we are dealing with in this specific case. So with the first iteration, because we chose the element to be Queen, so now we have Queen in its own set, Cartesian product with omega 2, and the parameter of omega 2 is going to be basically the same as what I'm given with, Queen, King, 2, and 9, except Queen is not going to be in it. Okay, so we have only King, 2, and 9 in it. Okay, and I'm just matching the parentheses, making sure that I got all of them. There we go, that's the last one. So that's the first iteration. Okay, and then in the second iteration of the loop, we will bind the element, the unknown E or the variable E, to another element of the set that we're dealing with. In this case, it's going to be King. And also, since we don't really have a T here, I just have to change this to Queen, King, 2, and 9 as well, because there's no T. T was, the variable representing this particular set, but since this time we are dealing with a specific set, then we don't use T anymore. We just use the set wherever T is referenced. Okay, so in this case we have chosen E, King to be E. So now we have King as in the singleton set, and then Cartesian product that with omega 2, and this time we're looking at the original set, except King is no longer an element. So we got Queen, 2, and 9 in that particular set, and then we close the parentheses.
Wait, why are we using omega 3 and omega 2?
That has to do with the recursive definition, because omega I of T is the union of blah blah blah. So here we have omega I minus 1, and therefore the 3 becomes a 2. But we also have T minus E, and that's why the the set that we feed to omega 2 are just one element smaller compared to the original set.
Gotcha. Okay. Yeah, I understand that. That makes
Okay.
sense.
And of course, all of these components are joined by the union operator. Okay. And now we have E being 2. And now, obviously, the order is not important because in the set there's no actual ordering, but I'm just using the order as the elements appear in the set. But there's no need to actually follow this order. I just want to do it in a kind of systematic way, so this way I don't forget a particular one. And the last one is when E equals to 9 and becomes 9 in a singleton set. Cartesian product with omega 2, and then we have king, queen, and 2 in this case, in this particular set. Yep, okay. So close that, close, like so. So, so I just want to see if there are any questions regarding how the original, okay, what we want to figure out, which is the omega 3 of queen, king, 2, and 9, is expanded into the big U notation, which is on the second line. Okay.
That makes perfect sense.
Okay, perfect. And then the more difficult one is how we expand the big U notation, which is basically implicitly a loop to loop through all the elements of what we are given with, into the 4 components that are joined by a set union operator. So are there any questions regarding that?
So the U, E, N, Q, king, 2, 9, E, omega 2, queen, king, 2, 9, minus E is the same as the 4 lines below it.
Yes. So basically, I am just unfolding a loop. This is basically, a loop, implicitly a loop. And then for each iteration, we generate a component that will be used in the overall union operator. So so in other words, you look at this as a loop, like a for loop in C and C++, and this is basically what you would see in a debugger on a per iteration basis. So I'm just, yeah, sorry?
Yeah, that makes sense.
Okay, excellent. All right, so I'm just double checking on the text channel to make sure that I'm not missing anything. All right, well, today we only got 2 people on the in the synchronous session. I guess must be because of it must be because of election day. People are going to. Yep, it is election day, and I bet you some people are reading the ballots really carefully right now, and that's why they cannot make it to the synchronous session. I don't know. I mean, that's a possibility. All right. So now we look at this and go like, darn it, we don't know how to generate this particular Cartesian product because we know what Q is. Okay, one side of the Cartesian product is just a singleton set like this, right? It's a set, but with only one element in it. So it's pretty easy to figure out what kind of tuple is supposed to be generated if we know what is on the other side. But we don't really know what is on the other side because it's an omega 2. So now we say, okay, fine, how do we figure out omega 2? So with the first one, we have omega 2 of king, 2, and 9. And then once again, we also look up the definition and we ask, can we stop the recursion already? Well, the answer is no, because the only time we can stop the recursion is when we are down to omega 1 of something. And when we look at the what we have right now, it's omega 2, so we cannot stop the recursion yet. So if we don't stop the recursion because we're at the quote-unquote base case, then we have to go for the recursive definition again. Except this time, I equals to 2, so I minus 1 is 1. Okay, so now we go back to here and go like, okay, fine, we're going to expand this again using the big U notation. So this time we have E in, and you can see that we have a smaller set this time. We only have king, 2, and 9 this time. And then for each iteration, we have E again. So basically E, you can look at it as a local variable. So this E has nothing to do with the other E, because now we're in a nested portion of the loop, if you want to see it that way. And then with this omega 1, we are starting with just 3 elements to begin with. And because E is already chosen, okay, to be a particular one, so we can now say, okay, we can use any one of these 3 except for E. So we have to say here minus the set of E here. And you have to be careful that we cannot just use E without the curly braces. The reason why this E, needs the curly braces around it is because the subtraction operator only work on sets. Okay, so whatever is on the left-hand side and whatever is on the right-hand side, they both must be sets. And E itself is not a set, so we have to use the curly braces to turn it into a set. Okay, so that's kind of important. And now we do exactly the same thing as last time, which basically means we are unfolding the loop into the iterations. So now we got E equals to king for the first iteration, E equals to 2 in the second iteration, and then E equals to 9 in the third iteration. So whatever product we come up with for each iteration, we basically make a big union out of all of those individual items. All right, so we look at the first iteration when E is king, and now we say, okay, what do we do? Well, we just go ahead and apply this portion of the equation, or it is already written here. So we basically just apply this, okay, for each iteration. For the first iteration, we need to figure out what is king as a singleton set, Cartesian product with omega 1 of, so this time, king cannot be a part of this particular set because we are saying king 2 and 9 minus whatever E is, and in the first iteration E equals to king, so king can no longer be a part of this set. We only got 2 and 9 left in this case. So close curly brace, close paren, and then one more paren right there. Okay, so we're going to union this with this, the result of the second loop, or the second iteration of the loop. So in the second iteration of the loop, E equals to 2, so we create a singleton set of 2 and then use a Cartesian product operator to connect it with omega 1. But this time the set can be king 2 or 9 minus 2. So 2 cannot be a part of this set, so we only have king and 9 left. So, yeah.
With Q sub I, do we go down to 0?
No. So we'll see, because at when I equals to 1, we can stop, because the recursive steps says, hey, if I is 1, we know exactly what to do with it.
Okay, cool.
You can change the definition so that you can stop only when I equals to 0, but there's no need to do it that way. So I'm going to show you what I mean by that. Okay, so we have E equals to 9 in this case. So 9 as a singleton set, Cartesian product with omega 1. And this time we have king and 2 as the set of the recursive call. And close, like so. All right, so getting back to when we can stop, you can always kind of change this definition a little bit and say we can stop when omega 0, when we're dealing with omega 0. So omega 0 is kind of interesting because it is the outcome set when we do not have any trials, right? So that means, the output of omega 0 is going to be an empty set. Does that make sense? Because
again?
Okay, so so here's the question. You have you have 3 items in the bag, okay, A, B, and C, and the experiment is me telling you and say, don't choose anything out of that basket, and then the question is, how many outcomes do we have in that particular experiment? So you might want to say 0, but that's actually not the answer. The answer is 1. Okay, there's one outcome out of that thing, which is basically there's nothing in it. So you basically end up with an empty tuple. Let me express that. Give me a second here to start up a text window so I can actually type this in a whiteboard with proper formatting. So give me a second here to rearrange this. All right. So we'll do an nvim of temp 2020 1103 CISP440.md, and I move this tab right next to where we are. So this way it's easier for me to go back and forth. Okay. All right. So here we go. So if you want to, you can actually define omega 0 like this. So we have omega subscript 0, and omega 0 is basically the outcome set of an experiment that has 0 trials. Okay, so we'll say, okay, let's apply this to whatever t is a set is. So the question is, what is the answer to this question? Okay, so let me basically ask the question in English again. So we are looking at the outcome set of an experiment. The experiment has a set T, which may or may not be empty, of items they can choose from. But the trick is we only have 0 trials in this case. Okay, it is.
So
yeah, go ahead.
If we have 0 trials, that means we can't put our hand in the bag, so the answer would be 0, right?
Well, but it cannot be a 0, because remember, this is an outcome set, which means whatever is the answer has to be coming out in the format of a set like this.
So it would be a set of nothing.
Well, would it be a set of nothing, or would it be a set of one thing in it, and it is an empty tuple?
No, that.
It is an empty tuple, because it has to be a tuple, because we are selecting things and ordering is important. But it's going to be an empty tuple in this case, because I didn't get to choose anything, right? So it is a sequence, except it's a sequence that has nothing in it. There's a major difference between there is no sequence, which will basically be an empty set in this case, versus it is a set with one item in it, which is an empty tuple. Okay, so let me just kind of put this, on the second line. So I'm going to put this in one bullet point, and then put this one in a different bullet point here. So the different bullet point is basically saying, an empty set is really not the same as a set that has an empty tuple in it. Does that make sense to you guys?
Yes.
Okay. So in this case, we need a set with one item, and that item being an empty tuple. I know it is if you talk about this in an English class or a philosophy class, it basically is just a debate of how you look at things. But in this class, okay, this is the only correct answer. It cannot be an empty set. So if we change the base case to be like this, okay, and we get back to the problem that we are trying to solve right now, okay, so this is how I defined it previously. And let me go back to my text editor here. So now, we need to go down one step further, because we need to figure out what is omega 1. So using this way to stop, okay, we will stop when we get down to omega 0. Let's see what's going to happen here, okay. So now let me move this so that we can see what omega 0 looks like, and that works. So there we go. All right, so now we need to figure out what is omega 1 of let's see, 29 Okay, we are talking about this specific case. Okay, we have omega 1 of the set that has 2 and 9 in it. So we look at this and go like, okay, what should we do about this? Now this time, remember, we are using omega 0 to stop. So now we have to look at this. Okay, excuse me, my own phone is, oh no, that's my landline ringing. So can you guys hear who was calling?
Doesn't sound very important. Oh, I'm getting a call from the same person.
I think it's some kind of credit company trying to call me. Probably we're trying to repo all my graphics cards and all the mics and everything else that I need for my classes. No, I'm just kidding, but it was a good one. All right, so we reapplied the recursive definition. Okay, so the recursive definition says, this is going to be, okay, let me put it on a separate line. It's going to be a big U notation, excuse me. And then in the loop, we iterate through all the elements of the set that we are given with in this particular invocation. And when E is bound to a particular element in the set that we're given with, then we generate E and then the Cartesian product with omega 0 this time, right? Because in this case, I equals to 1, so I minus 1 equals to 0. So this time we have omega 0. And what do we do with the set in omega 0? Well, it's whatever we're given with minus the set that has only E in it, okay? So now we go through all the iterations. There are only 2 iterations this time because there are only 2 elements that are given to me, and each iteration is just looking at one particular element in the set. So now we expand it and say, okay, what if E is just 2? Okay, if E is just 2, then we are looking at 2 as a singleton set, Cartesian product with omega 0 of 2 and 9, except 2 cannot be in it, so we only have 9 left in this case, like so. And that needs to be unioned with the next item, which is when E equals to 9. And when E equals to 9, then we have 9 in the singleton set, and then Cartesian product with omega 0. And this time, between the 2 and the 9, I cannot have 9 in this particular set, so we only have 2 left, okay, like so. So are we doing okay so far with the expansion of omega 1 of 2, 9 in a set?
Yes.
Okay, excellent. Now, yeah, go ahead.
Right. So then the next one, omega 0, it's just going to be omega 0 of a set of an empty tuple?
Well, it doesn't matter whether it's an omega 0 of an empty set or a huge set, because omega 0 of whatever is going to give you a set of one item, and that item is an empty tuple, because that is how we defined it over here.
Right. So we're just going to ignore the 2 and the 9 then.
Well, yes, but there's a significance to omega 0. So I'm going to basically, I'm going to finish this entire thing. In other words, I will do the recursive call, by hand, and then we use the return value of the recursive call back into where the recursive call is in order to finish all the calculation. But I just want to make sure that people understand, why omega 1 of the set 2, 9 expands eventually to this particular form. It's the same mechanism why omega 3 expands to this, why omega 2 expands to this, and now we have omega 1 expanding to this. So are we good so far?
Yep.
Okay.
And in reality, all of these expand even further, because you could also take with E is the king for omega 3 or equals 2 for omega 3 or equals 9, and then you'd replace
right. So in reality, it's very tedious, because right now this is the original problem, okay? The original problem is omega 3 of queen king 2, 9, okay? But I'm only looking at one of the 4 entries corresponding to the original omega 9. I take this one, and say, okay, what is that gonna look like? So I look at that specific one and say, okay, let's just look at this one, and that end up with 3 components. And then of the 3 components, I just pick the first one and say, what is that going to look like? And at this point, I look at this one, and it's going to look like this. So this is a very, very small portion of the overall thing. I'm chasing down the recursive call, basically step by step. Are we good?
Got it.
Okay. So now we get down to omega 0, and this time we have a 9 as the set that is given to me. But then I look up the definition and go like, hey, we can stop the recursion now. Okay, we are now down to omega 0. So we just say, hey, this one is pretty easy. I don't have to do any computation, because it is by definition, whenever we get down to omega 0, it's always going to give us a set of an empty tuple. Is that okay? So now what we do, yeah, go ahead.
Yes, that makes sense.
Okay. So instead of replacing something that I have already typed, I am going to copy and paste it, except this time I replace omega 0 of 9 with whatever is supposed to return, which is a set that has an empty tuple in it. Is that okay? And then, yeah, go ahead.
Yeah, it makes sense.
Okay. So the next step is to say, but we're not really quite done yet. Okay, tell me what is omega 0 of the set 2. Okay, come on, this is getting boring, right? Because we have already talked about how omega 0 of whatever is always going to give you the set that has an empty tuple in it. Okay, now we take that and we go back and substitute omega 0 of 2, or the result of that, back into where it is referred to in the first place. So now we have a set that has an empty tuple in it, like so. So now we look at this, okay, the E equals 2 is mostly just for documentation purposes, so for the most part, this is actually useless as far as, how we do the computation is concerned. I just put it here as a comment so that you know why we have that component. So we look at this and go like, that is rather silly, right? I mean, if you look at 2 Cartesian product with an empty tuple, what do you get? Okay, we get 2 back, but not exactly just 2, right? Okay, so let's go back to Cartesian products. Okay, so I'm just going to use AB Cartesian product with 0, 1. Exactly. Okay, so but I do want to kind of go through this again, just so that people remember what Cartesian product is going to do. So it basically creates tuples where the first item comes from the set on the left hand side, and then the second item comes from the set on the right hand side of the Cartesian product operator. So with this one we get A0, A1, B0, and then we have B1 over here. Okay, so that's how Cartesian product work. But this is a very strange case, because we are looking at a singleton set on one side, a singleton set on the other side, but we know the result is going to be a set of tuples, at least one tuple, okay, possibly tuples, but in this case it's a one tuple. So it's concatenation, right? Because it's I mean, Cartesian product is in many ways similar to concatenations of a string or a list, okay? Because we're basically saying, okay, we'll take this on the left hand side, we'll take this from the right hand side, and we're gonna join them, okay, as a tuple. So now we look at this and go like, okay, so technically speaking, okay, depending on how you want to look at it, so technically speaking, this should be a 2 tuple where 2 is the first item of the 2 tuple, and then the second item is an empty tuple itself, okay? Because this is one way to look at it. Because after all, this is an item, and we are basically saying this item is the second item of a 2 tuple, So the correct interpretation, or in this case, one interpretation, is to basically put this empty tuple here as the second item of the overall 2 tuple. So we're going to keep it like this for now, okay? And then we say union with the other one is going to look about the same, okay? So we have 9. It's going to be a 2 tuple where the first item is a 9, and then the second item is going to be an empty tuple itself. Close the 2 tuple, and then close the curly brace. So you can see how this particular way of looking at a tuple is going to end up with a lot of parentheses. Okay, we're going to have a tuple where the second item is a nested tuple, and we're going to nest this all the way to the top. So that means we are going to be looking at a very strange looking structure. It's basically each item is kind of like a tree because it has got a left and a right side to it. Except one side is always, it's going to be very lopsided. Okay, in other words, the left hand side is always going to be a particular value, and then the right hand side is always going to be a tuple that only has one item in it, but it has its own left hand side and right hand side. So instead of looking at things like this, we can now flatten the whole thing. So when we flatten when we flatten tuples, we're basically removing all the parentheses, okay? Well, all except for the outermost pair of parentheses. So we now just look at this as 2 as one single tuple, and then the other one is just 9 as a single item tuple, like that. And once we perform the union, then we end up with 2 in a single as a single tuple, and 9 as a single tuple as the only 2 elements left in this case. So I'm going to pause here, okay, because I do want to make sure that everybody understand how we got from omega 0 of something back to omega 1 and end up with this as omega 1. And aside from the definitions, I also want people to kind of think about this and make sense out of it as well. Because what omega 1 to 9 as a set is asking is, give me all the outcome sets where ordering is important, and we want to, let me see how to put it, and we want to, and this is an experiment with one single trial. So kind of imagine that you have a box, okay, where I give you 2 pieces of paper. One piece of paper says 2, and the other piece of paper says 9, okay? And I'm asking you, okay, how many outcomes can we get out of experiments? Okay, then you ask, okay, what is an experiment? And I say, well, each experiment has only one step, okay? And that one step is to pick a piece of paper out of this box, okay? Then go like, well, that's pretty easy, okay, right? Because I just need to pick one thing out of the box for each experiment. So you say, okay, having a 2, as the outcome of the entire experiment that's one, and then getting a 9 is the other one. So the only tricky part is, yep, we got 2 and 9 as elements out of the outcome, but we also have to make sure that we are using the tuple notation, using the parentheses, because it is nonetheless a sequence. Even though there's only one item, it is still considered a sequence, because otherwise the nesting of these things won't work. So I'm gonna give you guys a little bit of time to ask, if there are any questions about what we have done so far.
Yeah, it makes sense. It's going to take a while to write it all down. Could you put that into the text chat?
Yeah, I can do that. But there may be more things coming along, so I'm going to save it first, and then I'll post it at the end of the class. Or I can just kind of save it incrementally and post whatever is saved at this point. Either way is fine. Okay, so Alex is saying, so omega 1 is sort of like that, except everything in T is now a single tuple by itself. But yes, so the idea is, when you look at, how I define omega 0 and how omega 1 turns out. So omega 1 is really just taking a set of items and then turning each item into a single item tuple and then return the resulting set. So it's kind of the same thing as just returning whatever is given, with a minor difference that, each item becomes its own single item tuple instead of just the item itself. But that's a minor thing. We can just kind of, mention that, every item becomes its own single item tuple when we return it. Okay, excellent. So let me post what I have at this point just in case I forget, because I do forget things from time to time. And this is supposed to be, oh, I saved it in the home folder. I thought I saved it in the temp folder. I forgot to specify temp. There we go. Okay. All right, so there we go. So we have the text file. I might be adding more to the text file. In fact, I am going to add more to the text file. So this is just a snapshot. All right, so now we go all the way back to here and go like, oh, okay, so we eventually figure out what is omega 1 and of 2,9, and then now we say, okay, where is that going? And now we basically go back to here. Okay, this is where omega 1 of 2,9 actually goes. So we take this portion. Okay, let me go back to the beginning. So this is not even omega 3, this is just omega 2 of something. So we copy and paste this all the way down here. And then we say, oh, wow, we have just resolved what is omega 1 of 2,9. Okay, so omega 1 of 2,9 is this. Okay, so we copy that. And then we replace this portion because, that's basically the value that we have resolved to. So now we got this resolved. And guess what we're going to do next? We are going to go ahead and resolve this. Does anyone want me to kind of go through all the recursive calls to do this? Or are you guys okay and just say that, yeah, we know it's going to be k as a single item tuple and 9 as a single item tuple and those two things in the set. So are we okay with skipping the recursive call tracing of omega 1 of king and 9?
I hope that he makes those
Yeah,
Okay.
I'm fine with that.
Okay, excellent. So I'm just gonna say, oh, this is going to be just king as a single item tuple and 9 as a single item tuple, and then the two items in a particular set. And this one is just going to be a set where we have king as a single item tuple and then 2 also as a single item tuple, and the two of them in the set. All right, so now we can actually do the Cartesian product because we know what we are joining. So now the whole thing is going to become, the first line becomes king 2 as a 2 tuple, king 9 as a 2 tuple. The second line is going to be 2 king as a 2 tuple and 2 9 as a 2 tuple. The third line is going to be 9 king as a 2 tuple and 9 2 as a 2 tuple. So are we good so far? Because I'm just performing the Cartesian product and doing the flattening afterwards. Because if I don't do the flattening, then the second item is going to be its own single item tuple, which is one way to look at it. Structurally, that's exactly what it is. But from our perspective, we can flatten it and just say that the nested tuple is not necessary. Okay. So now we take this and go like, okay, let's make a union out of these things. But since every single item in each set is really unique, so that means the actual union is going to have all 6 items this time. So I would do kind of the lazy thing, just kind of copy and paste, and then just remove items, remove things out of it. So I'm going to remove that, and
I'm gonna leave.
because the union is not really doing anything, we don't have any overlaps between the sets. So the union is really just saying, okay, whatever each set has, we'll just kind of put it into the overall collection of items. All right. So now we have resolved what is omega 2 of king 2 and 9. And then we go like, okay, where did we see this? Why are we even bothering with the omega 2 of king 2 and 9? So the omega 2 of king 2 and 9 was originally here. So we take this and then copy and paste it all the way down here. And then we say, oh, we know what this item is now, okay? Because that's exactly what we have just resolved. So this particular set of 6 items, 6 2 tuples, is exactly what this item is. So we now go like, okay, copy and paste. We are done with the first line of the original omega 3. So what we do next is to do the same thing with the omega 2 of queen 2 and 9, and then we do it with the omega 2 of king queen and 9, and then last we do the omega 2 of king queen and 2. So are we kind of getting the hang of this?
Yeah, I think we're good.
Okay. If you think you're totally bored, that's actually a good thing, because that means you're actually starting to understand the mechanism, and you're understanding how we're basically reapplying the same thing over and over again. So the real important key here is the recursion, and also when we can stop the recursion. So this is the one way to do the stop the recursion. Basically, we're just stopping the recursion when there are 0 trials, because if you say that you cannot do a single thing about this, and then you ask me what is the outcome, I go like, hey, there's nothing in the sequence, but it is still a sequence, and that is the important part. In the notes, I kind of took the shorthand or the shortcut. Okay, I took the shortcut and just say that well, let's go ahead and stop when we get down to omega 1 instead of omega 0, because that basically saves you one recursive call that serves absolutely no purpose whatsoever. Okay. All right. So now that we have done this, manually. Okay. So let me just go ahead and save the file again. Control S, and then re-upload that file over here. Okay. So this way we have a snapshot of everything that we have. There we go. So now the question is, we can do this by hand. How do we do this using a program? So that becomes the next question.
Literally press the G button. I don't know.
So what do you guys think? How do we do this, as a program? Now, you just also keep in mind that you can use any programming language that you want. Okay, so given that is the case, how would you do this?
I would make either a vector or an array, and then I would have the language loop through said vector or array. Or I wouldn't loop it, I'd have it iterate through the vector or array. And then
right, so you probably want to use a programming language where arrays do not have a fixed size, because in C and C++ it's pretty rigid. An array needs to have a particular length, and so it's not as handy. Other languages like JavaScript or most scripting languages allow you to concatenate arrays really easily, so you don't have to do a lot of mumbo jumbo just to extend an array by one item or anything like that. So that is so that's basically how you can do it, and you just have to kind of look at the I here also as a parameter. So you basically have 2 parameters passed to omega. One is I and one is the set T. And of course now it becomes a question of how do you implement set operations, because we have a few set operations here, We got a union. Okay, we have to perform the union between different sets. We have to perform Cartesian products, and we need a subtraction between the sets. So those operations also somehow need to be implemented in this case, and
But he also does 350.
depending on what the set has to begin with, there are shortcuts. Okay, so so the next part of today's lecture, let's see, what time is it? So we got about half an hour. Okay, so the next part is to talk about a little bit about how we can represent a set. Okay,
That's
now
not balanced. That's
I also want to give you guys a
filling an entire group of
restriction
things for the
first,
sake
because
of
the more restrictions we know about what we need to represent, then we can use solutions that are actually simpler in real life. All right, so let me go back to the text editor here. All right, so let's just assume, okay, assume that the largest set we can have. Okay, so assume I'm going to give it a symbol here. So we're going to say, let's call it x here. Okay, so x is representing the largest set that we can have. Is really just a set of integers. Okay, and those integers start from 0, and it can all go all the way to, let's just say, 31. Okay, so given this particular restriction, every single set that we have to deal with is only going from 0 to 31. Okay, what would be a way to represent a set?
Bracket 0, 1, 2, 3, 4, 5, 6, 9, 10, all the way to 31.
Okay, so that's one way to do it. But that way of doing things is not going to be, well, first of all, it's not very compact. Okay, in other words, you're using at least 8 bits to represent something that can be represented by one single bit.
It's just a challenge.
So one way to look at this is to say, okay, so we can use each bit of a 32-bit, I'll just call it unsigned, just so that I don't have to deal with negative values. So we're going to use 1 bit of a 32-bit unsigned integer to represent the absence or presence of an element. Okay. All right. So what does that mean? Now, the best thing to talk about this is to give you guys an example. Okay, or examples in this case. So let's just say that I need to use designations here. So let's use let's use P as a set. Okay, so let's just say that P as a set is 5, 0, and 2. Okay, it's representing the inclusion of the elements 5, 0, and 2. So it does meet the requirement that it is a subset of X. Okay, because it has everything in P can also be found in X. Okay, so that's kind of the restriction. Okay, we are only dealing with a set where the set can only be a subset of X. So now what is going to be used to represent it? So the unsigned integer to represent P is going to be 2 to the power of 0, which is 1, 2 to the power of 2 is a 4, 2 to the power of 5 is 32, and you add all of these values together, then you get 37. So the number 37, or the bit pattern of 37, is used to represent the set of 0 to 5. Is that okay? Do you guys can you visually see what is going on here? Okay, so let's look at 32 as a 32-bit number. It's going to be pretty long. So we know that we have a whole bunch of zeros as the most significant digits. So as a 32-bit number, until we get down to bit 5, everything is going to be a 0. So we have zeros, 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 zeros. So that takes care of 16 bits. We have 16 left. Now we have 12 left. Now we have 8 left. So when we have 8 left, we have to be careful because this is bit 7, bit 6, this is bit 5, this is bit 4, and then this is bit 3, this is bit 2, this is bit 1, and this is bit 0. That is a base 2 number. So now we look at how we arrange the bits, okay? And we can see how bit 0 has a 1 to represent that 0 is an element of the set. We look at bit 1, which is a 0. But we can see that 1 is not an element of the set P. We look at bit 2, which is this one over here, and bit 2 is a 1, so that means 2 is an element of the set. And we can see how bit 3 and bit 4 are both zeros, and that's because they're both absent from the set. And we can see how bit 5 is a 1, and that's because it is an element of the set. And then the rest of the bits, okay, from bit 6 all the way to bit 31, they're all zeros because they're all missing from the set P. So are we getting a kind of understanding of how I am proposing to represent a set that can only have values from 0 to 31 as integers using a 32-bit integer to represent it?
What? Sorry, how did you come up with the 5, or why did you choose 5, 2, and 0?
That's just random, just as an
Okay.
example.
And then I'm confused how you got from the 520 to the 1432. I understand the 37 goes to
Okay.
that.
So let's relook at this, okay? So what exactly is the 1? Where's the 1 coming from? It is 1 left shifted 0 times. What about the 4? The 4 is the 1 left shifted twice. And what about the 32? It is a 1 left shifted 5 times. Do you see the 0, 2, and 5 in the set are actually being used to indicate how many times we need to shift 1 to the left-hand side?
Gotcha. Sorry, I'm so low rusty on bitwise operators like that.
Yeah, well, this is one of the reasons why they're really handy in some cases. Now, because we know that we cannot have duplicate items in a set, right? So that means, whatever we're adding here, the amount of left shift have to be different. Now, because every time we do a left shift, we end up with a number with only one of the bits being a 1. And if that is the case, we don't really need to do a full up addition. We can instead use a bitwise OR operator. This is a bitwise OR. 2 vertical bars is a logical OR. 1 single vertical bar is a logical is a Boolean or bitwise OR. So these are all really interesting stuff, because they're extremely efficient in terms of both computation and also in terms of storage. Because instead of using 3 items to store this particular set, and if you're using linked list, okay, that gets super expensive, because even though each item can only be an integer, which can be represented in 32 or 64 bits, as a linked list, you need an address to the next item. That's also another 64 bits. So if you're using a linked list structure to implement this particular set, it's going to take up at least, let's see, we have 64 bits is 8 bytes, and then you need 16 bytes per item. So 16 bytes times 3 is 48 bytes. So to represent something like this using a linked list will take 48 bytes, as opposed to this representation, which is taking up 32 bits, which is only 4 bytes. So you're looking at 48 versus 4 bytes.
Why do you have the parenthesis 2 at the end?
Parentheses toward the end. You mean here?
Yes.
So I use parentheses 2 to indicate the number is in base 2.
Oh, okay.
I know it's obvious, but because all you see are zeros and ones, but it is kind of important to make sure that people understand we're talking about a base 2 number.
Instead of like base 10 or something. All right,
Instead
cool.
of misunderstanding as base 10, right? Exactly. So if this is how we represent a set, okay, what are we going to do with, let's say, a union, okay? So let's say, let's say variable x represents, set P. Let y represent, oh, bad grammar here, represent set Q, and let z represent P union Q. Okay, so how do we get z?
No, here's what you do.
How do we compute z in this case? So let me just rephrase the question, okay? X is a 32-bit number representing a particular set P. Now in this case, I don't even need to know what are the elements in set P. I'm just saying that X is a 32-bit number, and I'm using this particular method, which is also called bit mapping, to represent P, and Y is representing Q, and I need to know what is the union of the two. All right. Well, okay, so it is not an AND, because when you have an AND, it means, in order for Z to have a 1, both X and Y must have 1s at a particular bit position. Okay, so AND serves a purpose, but not when we want a union. A union... Sorry?
Would it be the single OR?
Yep, it will be the single OR. Very good. Okay, so X single OR Y, which is X bitwise OR with Y, will give you a union. And this operation is super fast. Most processors, in the arithmetic and logic unit of most processors, this is a single clock operation. It's like really fast. To talk about this as a single clock operation really doesn't really convey the idea of how fast this is, because most processor cores today have multiple ALUs, and they can all do computations at exactly the same time. So that means if you can schedule the calculations of things, in optimizing the utilization of the ALUs, this is, you can do this, z equals to x or y, and a whole bunch of other integer arithmetics all at the same time. In other words, if you can schedule the calculations, in a very optimal way, this is quote unquote less than a clock of time. As opposed to the other way, using a linked list, then you have to kind of cross-check everything. Okay, this is what I have. Do you have that too? That's going to take a lot longer, because it is it's big O of n, big O of the number of entries in a set. Okay, so it's not going to be very fast. This is constant time calculation. It's like, bam, you're done. Okay, and what if you're downgraded to an Arduino? Okay, you're basically saying, okay, I need to implement an algorithm that makes use of the concept of a set, but I want to do this on the tiny little Arduino processor, which is an 8-bit processor running at 16 megahertz. Okay, it will still be fast. Okay, so that is why we want to look into mechanisms or representations that are super fast to compute, even with minimal resources. What about look at W? Okay, let W represent P, and then this time I have to type it out, intersection Q. So we're looking at the intersection of P and Q.
Would that one be the ampersand?
Yep, that would be the ampersand, which also takes a single clock on most processors. It is like, zoop, you're done.
What would be the case of XOR? That wouldn't be a union or a set.
So,
What would-
well, let's think about this a little bit, okay? So the XOR is actually not very helpful to us, okay? It doesn't map to any particular set operations that we want to implement, okay? So instead of looking at the XOR, okay, let's look at this. Let's V represent P minus Q, okay? So now, how would you want to do this? In other words, P minus Q is a set that has everything in P but not in Q. How would you implement the quote-unquote subtraction in this case? Okay, so let me just kind of comment here first and just say that this is a set of everything in P but not in Q.
Would that be XOR?
Well,
XOR is opposite of a union, isn't it? Because it's not a union, right?
yeah, you could use XOR in a very weird way as a part of this, okay? But I would rather not do that. All right, so let's take a look, okay? So we know that X is going to be in here somewhere, right? Because X is representing everything that is in P. We also know Y is involved in here somewhere because because Y is representing everything that is in Q. But we don't want everything that is in Q. We want everything that is not in Q. So instead of using an exclamation point, which is a logical not, we now need to use a bitwise not, which is a tilde symbol. Okay, it's the tilde symbol. Can you guys see that it is a tilde and not a minus?
Yes.
Okay.
It looks very messed up minus sign.
Yes, it looks like a very frightened minus sign. All right, so now we have these two components, okay? This is representing everything that is in X, and this is representing everything that is not in Y, okay? So now we want to say, oh, okay, so let's take a look at this, the English version first, right? Everything that is in P but not in Q, okay? We got the not in Q part, right? How do we translate the word but? Okay, does it map to anything that is a logical operator? As it turns out, it does, okay? Except it's not obvious. Because go ahead.
It would be and?
Exactly. So I could replace the word but with an and it wouldn't really change the meaning from a logical standpoint. It would change the way people perceive it, because the word but is emphasizing on the contrast. But in logic, it is no different compared to and. So now we have a bitwise and over here, and that's how we can perform, that's how we can compute everything that is in P but not in Q. And the trick is to utilize the tilde symbol, which is bitwise not. All right.
And is that in C in most languages like C and C++, or?
Oh yeah, these are universal to anything that is derived from C and C++. So you will find the same operators in JavaScript, Java, maybe Kotlin, which is kind of still more or less, based on Java. Yeah, so these are super fast operations too. I mean, most of these operations are single clock operations. Now this one here is going to be a 2-clock operation, because the bitwise not is one operation, and then the bitwise and is a second operation. But we are still talking about like super fast operations compared to the implementation, to a equivalent implementation using a linked list. And the worst you can do, with this kind of thing, is to utilize the template library of C++. Okay, have you guys already been exposed to the template library in C++? I think that should be in CISP440.
I'm not familiar with that name.
Oh, really? Okay. So let me just kind of give you guys a pointer, even though we are not going to use it in this class, but I think it is kind of important to understand what it is, and when you should use it, and when it may not be a very good idea to use it. So we're looking at what we call the C++ template library.
Is that where you use T to represent like?
Yeah, T in angle brackets.
Gotcha. Yeah. I didn't know that was the name, but yeah, we use
Yeah.
that in the books.
Yeah, so you can look it up and you can see that the C++ template library has the concept of a set. Okay, so we can perform basically all of the operations. This is how we can insert elements into a particular set. And let's see, does it show me all the primitives? I'm just trying to find out whether it has unions and whatnot. It has all kinds of iterators.
Wouldn't the C++ reference website be a better use to find all the functions?
This one is probably going to be the same. I think it's going to be not any better or worse than the other one. So it doesn't even give us the primitives of unions and intersections and whatnot. So you still have to implement all of those primitives using your own code, because the methods of sets do not include unions and difference and intersection, all the really kind of useful ones too. Well, that is really kind of unfortunate. Anyhow, okay, so let me get back to, oh, where did I put it? Down here. Here we go. All right. So now how do we put an element into a set? Okay. Well, let me put it this way. So I'm going to use uin32_t, to represent 32-bit unsigned integer. And to utilize this particular type name, you can actually do it. All you have to do is to pound includes stdint.h, the standard integer header file. Okay, this is actually it's a really good idea. Okay, regardless of what kind of programming you are doing, it is always a good idea to designate what is the width of the integer. Because if you want your program to be compatible or cross-compile capable across a variety of platforms, then you want to basically be able to specify exactly how wide an integer is. This will basically get you out of problems like, oh, but this program compiled and worked fine in a 64-bit architecture, but the moment I cross-compile that to a 16-bit architecture, it doesn't work. Well, guess what? In a 64-bit architecture, an int, just int itself, is automatically 64-bit wide. When you move the code and cross-compile it in a 16-bit environment, then an int is also by default just 16-bit wide. So because the width is changed, the range of values that it can represent is also going to change. So that's why programs that has been working fine when compiling on a particular platform can suddenly stop working when it is compiled in a different platform, because the width of the integers have changed. By using uin32_t, you're basically saying you're not letting the compiler to choose the width of the integer. You're spelling out and say, I want a 32-bit integer in this case. So this is actually a very useful thing to do, outside of the context of this class. So you might want to kind of start to incorporate this into your other programming. Go ahead.
In the case of like a long int, how does that work?
So a long int makes no difference whatsoever when you're compiling in a 64-bit environment. So whether you specify long int, just int, or long int, they all give you 64-bit integers, at least in GCC. If you're compiling in a 16-bit environment, I believe an int is 16-bit wide, a long int is 32-bit wide, and a long int is 64-bit wide. So the meaning or the semantics of how many longs you specify in a type changes depending on what compiler you're using, or what is the target platform of the compiler. And that makes it kind of really iffy, because that means a program that seems to work, you adjusted everything to make it work on a particular platform, will suddenly not work on another platform.
Gotcha.
Yep. So
But we have those install programs that choose whatever is the best compile architecture for the given computer.
there's that. I think most programs that need to cross-compile, they really should use these terms to begin with. The auto-config stuff, would make sure that you have the necessary libraries and header files. That's what they are mostly doing. But in terms of the code, the programmer, the developer, still has to make use of types that are platform independent.
Gotcha. Okay, that's cool.
Yep. Okay, so let's think about the empty set. What do you think an empty set is going to look like when I want to represent, a set as an integer, where every single bit is indicating the presence or an absence of an element? In other words, if I want to be super, frugal and say, I want to define what an empty set is going to look like, what do you think it should be initialized to?
0.
Exactly. Wow. Isn't that cool? Because if you want to know whether a set is empty or not, you just have to see whether the underlying integer representation is 0 or not. That doesn't take you any time, right? I mean, it's comparing to 0 is like almost a, it doesn't take up any time. So
the difference between empty set 0 and a set containing 0 is the first bit being 1, correct?
This is an empty set, which means it does not contain, anything. So a set that contains 0 as an element is going to have a value of 1. You are correct about that.
Oh, okay. Is that how null pointers work?
There's nothing null here. There's no null pointer here. Now there's a mystery surrounding the word null, N-U-L-L, in uppercase. Null is kind of defined this way. That is how null is defined. It's just a macro that expands to 0. But then somebody is going to say, but I can use null to compare to a pointer or to assign to a pointer. You can do the same thing with 0 without casting also. That is actually true. Okay, I'm going to give you guys an example here. Null pointer. And you can just initialize it as 0. The compiler won't complain. Living a lie my entire life.
This makes so much sense now. Oh my god, how did we not learn this earlier on?
Yeah, 0 is special. 0 as a numerical literal constant is special because it can basically be casted into all kinds of types implicitly. Now you cannot do this, okay? If you do something like this, your compiler is going to bark at you and just say that there's a type mismatch because null pointer is supposed to be a void pointer. Now I know a void pointer doesn't point to a particular type, okay, but it is still a pointer, and 25 is not a pointer. But 0 is special because 0 can cast to anything, any scalar. Okay, I should say it can cast to any scalar without a typecast operator. It can implicitly do that with most compilers. Now, I'm pretty sure there's a switch on a compiler they can turn on, and it will basically say, nope, we are now going to prohibit the implicit typecasting of 0. I'm pretty sure there's a switch that can do that, but if you're looking at a standard compiler, it should be able to do this without complaints. And one really cool place to kind of play with a compiler is, I think it's online GDB and not GDB online. Online GDB. Yep, there we go. So this is a really kind of cool website because you can actually sign in using your account. So I got mine already signed in. Even without signing in, you can just test things without having to install a compiler. It only works with single file programs, which means if you have multiple source files and a whole bunch of header files, this is not going to be a good way to do it. Okay, but if I just want to test whether the casting is going to work or not, I can just now say, okay, here's a void pointer, test pointer, and I just want to initialize it to 0. Okay, and then we go debug, because debug is gonna, oh, I need to select the language first, so we'll say C, and the program compiles just fine. Okay, I get into the GDB prompt. Now if you say, well, let's try the other one, right? Let's try 25 and see if 25 can automatically cast to a pointer type. Okay, so I change it, I save it first. Okay. Oh, okay. I don't actually save. I don't need to save it. I think I just need to debug it, and that will go through the compiler. So it does give me a warning this time. Initialization makes pointer from integer without a cast. So it turns it into a warning, but it really should be an error. But if I change it to a 0, I don't think it even gave me a warning that time. I didn't really pay attention to the messages. So let me try that again. Debug. Yep, that's right. Okay, so with a 0, it does not even bother to give me a warning. There's a switch on the compiler that can turn warnings into errors, which basically means it won't give you an executable, and you have to fix it before your program can run. But 0 is special. It doesn't need any casting to any other scalars. All right, so we are running out of time. Okay, but it is kind of important to look into set representation, because the next homework that I'm going to give you guys will require, well, okay, I wouldn't say require, but it is nice to have a set of primitive functions that can do many of the set operations. The other part, which is concatenation, not concatenation, Cartesian product, that is a tricky one too, because depending on how we want the outcome to be represented, you do not necessarily need to use Cartesian product. Okay, so there are ways to get around that problem. Yep, you can say int equals to null, and nothing bad is going to happen. The compiler won't complain about it. So let me just kind of demonstrate that too. So we'll say int I equals to, and it has to be all uppercase no, like so, and ULL, there we go. All right, so let's go ahead and debug this, and it's fine, not a problem. Oh, okay. Okay, so no is already having a pointer type associated with it. So there we go. It is, okay, so no is defined to be void pointer 0. I think that's how it's defined. The other way you can do, check this out, is to actually read standard io.h. So if you look at, okay, that's smart enough to do this. And you can just check out how null is defined. So the macro is the value of a null pointer constant. So null itself is not just 0. So I stand corrected because I said that was the case. But the point that I was trying to make was, 0 by itself is actually sufficient to replace null in most cases. So null, okay, to answer the question in the text channel, so I think this is how null is defined. It's defined null and a void pointer of 0. That, I think, is how it's defined. All right, we are out of time today, but on Thursday, what we'll do is to finish up this discussion, and then we'll have a programming assignment where I want your program to give me the omega something of a particular set. Okay, so if you do it correctly, if you do it using what we have learned so far, and also what I'm going to talk about on Thursday, it's actually not going to be too big of a deal. Okay, On the other hand, for people who want to store all the sets internally and then actually perform a Cartesian product, it's going to be a nightmare. That's all I'm going to say. So we'll talk about this on Thursday. But it is important to kind of go over the material of today, to make sure that we understand logically what is omega I doing, and also how we can implement set operations in C and C++. Then on Thursday, I'm going to give you the additional parts that you need to write functions in C or C++ in order to do what omega does. All right, prepping for a nightmare. Well, it's not going to be that bad, okay? It's just that we need to clear the concepts first, for today, and then on Thursday we'll have some additional concepts that will be helpful to implement omega. You can also start to think about it, okay? Just my advice is don't work on it yet, because there are tricks, okay, that can really kind of help to simplify the program. Oh, absolutely, I can update the text file. Let me get back to the text file first. Save, and then re-upload. There we go. And I'm not going to comment it this time, but I will pin it. So this way it's easy to find it. There you go. Cool. All right, it is noontime. I just overran the class by 10 minutes, and I'll see you guys on Thursday. And good luck with election day. I hope whatever you are, leaning on is going to happen. So we'll see.
Devil's advocate, I see.
Sorry?
Devil's advocate, I see.
Oh, that's who I am. I don't. I do want people to go to vote. Even if their ideology is different from mine, because that's the whole idea of a democracy. Well, that and serving in jury duty. All right, cool. I'm going to disconnect now, but I will be online for at least another hour, because that's my office hour. So if you do have questions about the stuff that we just talked about today, you can also talk to me over text channel. All right, good day, and I'll see you guys on Thursday. Bye.
Goodbye.
Bye.